Hello friends, this is Hemant Kumar Naik and I am going to present seminar presentation on the topic of bimetallic catalyst preparation for butane dehydrogenation. Right. So now I will share my screen to uh, this is my screen. I hope you guys can see me. Right. So let's start presentation. And myself, Hemant Kumar Naik, and I'm going to present on the topic of bimetallic catalyst for butane dehydrogenation. Right? Mm, I will enter searching for option. Now this is my topic bimetallic catalyst preparation for butane dehydrogenation. Uh, My presentation will proceed in this way. First, I will discuss some introduction, then motivation, problem statement, preparation method, results, and then conclusion. So this will. So let's start with the introductions. So, bimetallic catalyst, its importance are there because bimetallic catalyst provide better performance and have synergistic effect making superior to monometallic catalyst. So if you use bimetallic catalyst, then we can have better results. Right? So and bimetallic catalyst also modulates electronic and geometric effects. So, and we can see butane demand 2021-2031. Right? So, and its end use industries are automotive, aerospace, industrial, pharmaceutical, packaging. Right? So these are the themes. So basically, butenes are essential raw materials used to, to obtain polymers, right? And gasoline additives and other chemical products. And how we can produce butenes, conventionally secondary products in naphtha cracking unit and what process involves high temperature and pressure. Right? So it will be developed. So we look into catalytic dehydrogenation of butane, right? So because it is local butane, low temperature and pressure processes, and you can get the pure product by catalytic dehydrogenation of butane. Right? So this is the thing, and this is prediction of transparency and market research. I move next slide. So some motivation why we are looking for bimetallic catalyst. So it's basically it provide enhanced activity, selectivity, stability. And so if we were catalyst, we can have these advantages. And characterization techniques also development characterization because characterize the biometric character of particles much more. If you prepare biometric catalyst, so we can characterize uh, and like characterize the structure and composition of individual particles. Right? So basically, we'll any catalyst we look for size distribution, particle shape, particle size, yes, structure, crystallinity, and composition. So these are the uh, and also if you prepare biometric catalyst, so it is advanced, advanced. You can have advanced catalyst preparation. So this in this work, dehydrogenation of butane performed. So why dehydrogenation? Because uh, First is the demands of butene. We are and the light olefin like butenes or feedstock for valuable chemicals. Yes, in naphtha cracking process, also it is full. And then next is production of hydrogen. So here byproduct is hydrogen. So we can produce hydrogen as well. So now some problem statement. So because few studies on use of palladium as dehydrogenation or hydrogenation catalyst. That's why we are going for palladium. And data on dehydrogenation of butane or palladium catalyst is limited, right? So and we can see butane selectivity if we go bimetallic by gallium modified, so we can get 95% uh, selectivity, and for monometallic only 80%. So palladium based biometallic is particular interest for dehydrogenation, and the main thing is the metal precursor. So its metal precursor cost is low, and the next is electrolyte deposition. Whatever electrolyte deposition biometallic deposition is relatively easier and cheaper. So this is thing, and here preparation method. Right? So this electrolyte deposition method is used to prepare biometallic catalyst. So first preparation of supports is there. So for that we have to make aluminum nitrate solution, and then stirred at room temperature for 15 minutes. So after that, to maintain pH 10.5, we have to add ammonia solution, and after the 60-minute stirring at room temperature, we have to wait for 6 hours, right, at 75 degrees Celsius. And then next task is cooling, washing, and filtration. Right? So filtration is needed. And after that, whatever cake, filtrate cake is there, we have to dry in one at 100 degrees Celsius for 12 hours. We have to dry. And after that calculation to remove moisture and volatilize at 550 degrees Celsius for 6 hours. And in this way, we can produce aluminum oxide, Al2. So this is the support. And next is once we prepare to support, then we have to deposit metal into the support. So for that, we have to set filtration you set up, and after that, in Buckner funnel, we have to put alumina sample, and after that, uh, N2HO4 solution 20 ml have to pass on the alumina support, right? And and after that, uh, filtrate will be collected, and the palladium precursor solution of 20 ml we have to pass in uh, the support. So in this way, we can get palladium supported on alumina. So this completes first cycle, and after that, filtrate whatever filtrate is collected, we have to pass in same alumina, and right, so same whatever left we have to pass again, and then in the third and the fourth cycle, we have to again pass into hydrogen solution or reducing agent, TML, and then next task is platinum precursor solution of 20 ml. So in this in third cycle, we have to pass platinum precursor solution. Yes, in this, and after that, whatever filtrate collected in fourth cycle, we have to again pass, and in this way, we can produce palladium, platinum, alumina, supported and alumina catalyst. Right? So this is the basically bimetallic catalyst. So once we have prepared catalyst, then we have to go for its characterization. What means physical properties. So first is EDX analysis. This is in EDX picture. So in this, we can measure elemental analysis. Like we have different samples, yes, different samples, and first like palladium supernal alumina, uh, 1.1 palladium loading we can obtain from this figure. So and The next stage is like palladium, platinum, support and alumina. Platinum loading each comes out to be 1.4 and palladium each comes out to be 0.6 uh, and total loading will be 2%. Right? So this is also there. So this is basically this peak is for this sample. Right? So similarly, we can get different EDX images, but I have put this peak for palladium, platinum, aluminum. So this is the thing. Next is you have to measure also VT surface area. VT surface area. So for palladium, platinum, fresh catalyst, we can have 181 meter square per gram, and pore volume comes out to be 0.327. Average pore diameter which comes out to be 6 nanometer. Right? So similarly, uh, also TEM analysis is also uh, performed. Right? So average particle size to get average particle size. So in this way, palladium, platinum, alumina, average particle size is 4.3 and standard is 3 particle count. And it means 95 particle was there in the range of 4.3 nanometer, right? So this is a typical TEM images. So you can see morphology of the catalyst, and this is the cluster size, frequency versus cluster size. So mean cluster size is obtained at 10.4 nanometer. So weight improvements, palladium, platinum, supporting and aluminum at least. So here you can compare. This is typically PT isotherm, and this is pore size distribution. Two samples, one is weight prevention and one is this convention means electrolysis deposition, getting biometric catalyst. So pore diameter it looks like this, like uh, uh, in the range of mainly in the uh, range of 0.10 nanometer per cubic centimeter per gram. So, and this is the diameter in nanometer, and this is BT Jobson as of now. And this is this CP figures picture C each for XRD image here intensity versus to theta is there. So we can see peaks. Some peaks is obtained. So for alumina and biometallic at least similar peaks is obtained, which means catalyst is well deposited on the support, right? So metal is well deposited on the support, right? So this is the main uh, interpretation from this graph, right? Next stage, we have to perform FTIR to know acidity of the catalyst. For that, here transmittance versus wave number is there. So you can see some peaks. So this peaks is basically showing acidity of the samples. So right in the here, L is pyridine bonded to lace acid side. So L is the lace acid side, and C is for coordinative bound pyridine, and B is for pyridine bonded bronzed acid side. So whatever peak we can get in the range of 1450 and around 1450 and here in the range of 420 in the middle of 1450 and in between 1450 and 1500. So this is the interpretation of FTIR basically to know the acidity of the catalyst. So FTR again here COD option is there. COD option on monometallic platinum catalyst and palladium as well as biometallic. Right? So if Jordan's versus wave number is plotted here, so these peaks identify fewer jobs. Right? So, and next stage once the catalyst is characterized and prepared, and if preparation is well, then we can apply that catalyst to reactions, right? So here dehydrogenation activity measurements were performed. So one reactor were there, packed bed reactor at 550 degrees Celsius under atmospheric pressure. And so 0.25 gram catalyst mixed with 1 gram quartz powder and placed in center of the reactor. Thermocouple was placed in contact with catalyst bed to know the temperature. Basically, three gases were there: nitrogen and butane, hydrogen and nitrogen in the ratio of 1 is to 3 is to 6. Total flow rate is 100 ml per minute. So this is some picture which represents products and the reactant. So and this is the formula to get conversion data, butane conversion. So whatever moles of butane in minus moles of butane out divided by moles of butane in, and if you multiply by 100, then you can get conversion. Similarly, selectivity and yield also you can calculate by these formulas, and this is a typical reaction for dehydrogenation of butane, right? So let's conclude. So basically, in this paper, they have prepared biometric catalyst, right? And which shows superior performance in terms of conversion, selectivity, yield, and stability also, based compare with the monometallic catalyst. So the higher activity of allied platinum platinum metal resulted in higher conversion for biometallic catalyst. So lower acidity resulted in higher butane selectivity and stability of the biometallic catalyst by minimizing the picking and the secondary reaction. And co-deposited palladium platinum alumina catalyst shows the highest butane conversion of 50% at 600. So co-deposited is there in this first both the palladium and the platinum precursor solution were mixed, and then we pass into the support. So this is co-deposited and sequentially first palladium and then platinum. So which I have left at the time of discuss about catalyst preparation. Right? So two methods were there: co-deposited and sequentially deposited. Same catalyst shows highest butane yield of 42%. So this is basically dehydrogenation reaction and its results. In conclusion, and these are the references which I have used. And thank you. If you have any question, you can ask. Right? Now I'm stopping here. Goodbye. Take care. Good night.